Hi. All right, we're going to keep talking a little bit about Tony here. A little rotational momentum, also called angular momentum, when things are going in circles. Remember, linear you all know, is mass times velocity. So a rotational quantity that corresponds to that is going to be our I times omega. All right? Anytime there's an m, it's replaced with an I. Anytime there's a v, it's replaced with an omega. An impulse is a force times a time. That's a linear quantity. Now, for rotational, remember, we have a torque, and we will multiply that by a time. So a rotational equivalent of impulse is torque times time. And if you remember, force times time causes momentum to change a mass times a delta V. So the exact same thing occurs with this rotational quantity. So I can say, and a torque times a time interval is equal to an I times a change in an rotational velocity. Okay, and just the same thing as it is here. You guys all know this. I can solve and isolate a torque. I could also write this as, instead of an F, this would be a torque, then is equal to an I times our change in omega over a change in time interval. And exactly the same way that a delta V over a delta T can turn into a calculus, would be a differential velocity over a differential time. This could be the same thing as a differential omega over a differential time. But you guys all know the derivative of velocity with respect to time is an acceleration. So this is what you guys know. That means that a torque is equal to an I alpha, which is, again, some things we've already talked about. But please remember the link between momentum and Newton's second law. But a quantity that is an I times an omega is a rotational mole. So linear mole, it's a rho is mass times velocity. The symbol for rotational mo is funny, but it is a regular old capital L. So L is the symbol for Tony. Rotational angular momentum is simply known as L. So, same thing I said there. L is going to be I times an omega. That's Romo. That's Tony. I omega. Some things to remember when we talked about collisions, things are happening in straight lines. Things were banging into each other, or things were flying apart, collisions and explosions. So masses were changing is what I was saying. So if two items come together, their masses combine. That's an increase in m, which typically corresponds to a decrease in velocity. The opposite is true also. If two items are stuck together and they explode and they fly apart, then they're losing some mass from the mass hole, right? And they each have their own respective velocities. So usually in linear quantities, in terms of collisions and explosions, what we'll do is we'll say, hey, some mass changes, which results in a change in velocity. But with rho mo, the same thing is true, but it is the I's that could change, which could result in changes in omega. All right. Examples of this are folks who do diving, folks who do gymnasticating, folks who figure skate a little bit. But what this beautiful drawing is a figure skater that starts here. So this is B4, and then this would be B5. Okay, I'm going to say this figure skater is skating on some ice that's down there, whatever. The axis at which this person is rotating is right there, which means the axis they're rotating is right there. I'm going to say this person is coming out of the page on this side, so that would be the symbol for outa. and this is the symbol for enda, right? So this person's coming out of the page and into the page. So they're going in circles. They're starting to rotate. And so again, on this side, this person is going outa on that side, enda on this side. So again, that initial position where this person is starting to rotate around that point, her mass or the mass of that skater is spread out very, very widely. All right. So they're probably not rotating very fast. Then when that person tucks their mass in very close to the body, boy, they go nuts. And so the way you explain that is to say the amount of L before is the same as the LB5 before and after. So it's an I omega, and I times an omega is the same thing as an I times an omega. So it's really this simple. It's a big I times a little omega is equal to a little I times a big omega. It's that simple. If one gets bigger, the other gets smaller, and there you go. So here's another example. You remember what I did in our last video is I had Bob here, and Bob was going back and forth relatively slowly, but as soon as I grab Bob, and now he's going much more fasterly. And so there's a slow Bob, faster Bob. All right, so all I'm doing is calling it a pendulum that's changing length. Okay, so there's a longer pendulum, and the rate at which it's going back and forth is relatively slow compared to that. As you can tell now, it's going back and forth much fasterly. So I'm going to have this guy starting here with a certain M, and it has a certain L. Over here, it's the same M, but when I grab it right there and hold it by the string, what I'm going to call it is L over 2. Now, this is the different length of Bob, or a different radius, if you would like to call it that. But usually pendulas are referred to as L's. All right, so what I will say is the LB4 is the same as the LB5. So the I that it starts out with times the omega that it started out with will be the same as the I that it ends with times the omega that it ends with. Remember the I of a pendulum, all of the mass is just at the full length away. It's just ml squared. Sometimes it's called mr squared, but it should remind you of a circle, right? A hollow and empty ring or a shell. This has the same I as Bob. Okay? And so it's ml squared times whatever omega it was going back and forth at. If I cut that length of the pendulum in half by just grabbing the string like I showed you, then it's ml over 2 squared times its omega final. All right? So what you can tell then happens are those masses die, and I'm left with L squared times the initial omega. Over here, I'm left with an L squared over 4. Now I got to square the denominator times that omega F. And then you can tell, well, gosh, it also doesn't even matter what the length initial was. If I just cut it in half, whatever that L initial was, you end up with that on this side, multiply the 4 over. So the final speed at which that sucker goes back and forth is 4 times the initial velocity, and hopefully you can tell, well, gosh, that's pretty similar to the square of that change in length, isn't it? All right, now the third example I'm going to do in this particular one is what I ended our last video with. If I have something that starts like this and then ends up looking like the C-clamps way outside here. So what I'm going to have is a meter stick and 2 C-clamps. And I'm going to have them starting at a certain angular velocity. See what the final rotational velocity is. But that's what I want you to envision, just like in the previous video. The meter stick with 2 C-clamps. I'm sorry if you couldn't see the word C-clamps. All right, so before, I'm going to have those 2 C-clamps way out on the edge, all right, way out at 10 and 90. It'll be rotating around the 50 centimeter mark. Its initial rotational velocity will be 2 radians per second. Okay, so then what I'm going to do is have those two masses come much, much closer together, and I'm going to see what the final rotational velocity is. So this is the before condition. Then those C-clamps are going to go much closer to the axis of rotation. That should remind you of this figure skater here, because in this position, the mass is far out. That's where the C-clamps are way out at the 10 and the 90. Then when I pull those C-clamps in, the mass gets much closer to the axis of rotation. That should, it's the exact same drawing, just C-clamps on a meter stick instead of a person figure skating. All right, so again, conservation of Tony Romo. It's the LB4 is the same thing as the LB5. All right, now remember L is I omega. There's the sum of the i's with a little I means initial. Whatever your starting condition is times your initial rotational speed is going to be the same thing as the final I configuration, the sum of the i's final times their omega final. Now, the only thing I need you to realize is when you look at this situation, you should see three i's. All right, three i's. There's the eye of the stick, and there is the eye of clamp 1, and there is the eye of clamp 2. So there are three eyes involved in this. Do not cancel out the eye of the stick. All right, do not kill the eye of the stick. All right, so I have three eyes: the eye of stick, the eye of clamp 1 initial, the eye of clamp 2 initial, times its initial rotational velocity. That equals the eye of the stick times the eye of clamp 1 final, once it moves to its closer position, times the eye of clamp 2 final, multiplied by their whatever final rotational speed it ends up being. So I'm just going to divide the sum of the i's over, okay? So this will just be the initial speed divided by the ratio of i's. I. Now, remember, the eye of a stick around the center mass is 1/12 ml squared. And then these are just point masses. So I did that to equal the initial omega. I'm sorry, times the initial omega divided by those mr squareds, which again are clamp 1 initial, M clamp, radius clamp 2 initial. So that's what those stand for, the mass of a clamp times the radius clamp 1 final, the mass of the clamp times the radius of the clamp 2 final. All right, so, and just to remind you, what we ended up with, or saying is measuring before, the stick is 80 grams, the clamps are 220 grams a piece, okay? So I'm just going to go ahead and write this out here. So what we're going to end up doing is where the 1/12 ml squared is, I will have 1/12 times 80 grams is 0.08 kgs times 1 meter, that's the length of the stick, squared. All right, there's 1/12 ml squared. To that, I'm going to add the mass of clamp 1 times the radius, the distance clamp 1 is initial. The mass of clamp 1 is 0.22 kgs times its initial radius, which was 0.4 meters. I'm going to square that. To that, I'm going to add the same mass, 0.22 kgs, because they're the same clamp. It is also 0.4 meters away. I'm going to square that. So that quantity is the sum of the i's. I'm going to multiply that by 2 radians per second, because that's our initial rotational velocity. So there's our numerator. Then I'm going to divide that whole numerator by all of the i's, the three i's, which the eye of the stick still stays 1/12 times 0.08 times 1 meter squared. To that, I'm going to add the mass, 0.22 kgs times their new distance, 0.1 meter squared. And then I'm going to add that again, 0.22 kgs times 0.1 meter squared. So as long as that's in parentheses down there, the numerator has 2 sets of parentheses. That will be my omega F, all right? The final speed at which that sucker's going in circles. And that omega F ends up being not quite 14. It's like 13.9-ish radians per second, okay? That's its final omega. So again, when When those C-clamp C's come much closer to the center, that sucker goes nuts. When they're out farther, they go a lot slower, okay? In the next video, I will give you a little more information about Tony, and when things go in lines, they don't, they can still have rotational values, all right? But anyway, yay physics.